Thank you. Well, good afternoon and welcome to this installment of the California Dreams Microelectronics Hub's Technical Seminar Series. In this weekly series, we spotlight key technologies and advances being developed by scientists and engineers within our microelectronics prototyping hub and beyond. I am Mike Haney, the Deputy Director of the California Dreams Hub. Today, we're very privileged to have Professor Julia Greer from Caltech, where she is the Ruben F. and Donna Mettler Professor of Material Science, Mechanical Engineering, and Medical Engineering. Her academic background includes degrees in chemical engineering from MIT and a PhD in material science from Stanford. At Caltech, she is the director of the Kavli Nanoscience Institute. She is extremely active as a visionary leader in the nanoscience field, many awards and activities, including editor-in-chief of the Journal of Applied Physics. Among her many accolades is her recent election to the National Academy of Sciences. And she somehow manages to also be a highly regarded concert pianist. And in fact, her MIT degree included a minor in music performance. That's quite interesting. Today, her seminar has the intriguing title, Intelligentsia of Nano-Architected Hierarchical Materials. Julia, the virtual podium is yours.
Hi, thank you so much for this kind introduction. Can everybody hear me? Like you can nod your head if somebody can hear me. Great. Well, I appreciate this opportunity and thank you, like I said, to your for the wonderful introduction here. I am hoping to entertain you for the next 45 minutes or so, and I'd love to answer any questions you might have at the end of the talk. So yeah, let's begin. So here's the title, and it's a little bit provocative, Intelligentsia of 3D nano-architected materials. And you might be wondering why all of these words belong in the same sentence. So my objective is to walk you through and explain why that might be. So if we think to about 20 years ago, when we think about coffee, we basically, the choice is binary. So how do you take your coffee? Seriously, very seriously, you are either very tired or you get coffee. Now fast forward 10 years or so, and now the coffee can be distinguished by color. So it's either black or white. So this is real progress. And of course, now when you go to Starbucks, you get half calf, half decaf, double soy latte, etc. So this evolution of coffee drinking is foreshadowing this question of why can't we have the same level of customization in our materials world? So what I'm showing you here is a very busy plot, but it's some measure of mechanical attribute, and I'm choosing to show you strength, but it doesn't have to be strength. It can be toughness, it can be fracture, resistance, etc. It's some measure of mechanical resilience as a function of density. And all the colorful domains that you see on this plot represent all the materials that we know how to make today. And the picture that emerges right away is that we as a society are very good at making materials that are simultaneously strong and heavy, or lightweight and weak. And what we're not so good at is getting into the so-called white space, where the materials can be, when these properties can be decoupled and the materials can be made lightweight and mechanically resilient simultaneously. Now, this is a log-log plot, so even a small change or a small advancement within the space already represents a substantial change. So how do we get into that white space if everything we know how to make today is already represented here in these colorful domains? Well, the way we approach this is by introducing the concept of architecture into material design. When you look at these two structures, one of them is the largest man-made stone monument, the Great Pyramid of Giza. It stands about 150 meters tall and it weighs nearly 6 million tons. In contrast to the Eiffel Tower, which stands twice as tall, but it weighs 3 orders of magnitude less. And as far as I know, both are still standing. And what that tells us is that by properly structuring or architecting our material, we can get away with the same mechanical resilience without using quite as much material. And so this is where we started our research, and I can't believe this was about 15 years ago now. So what you're looking at is the world's most normal dandelion. It's not, there's nothing photoshopped here. And what we're showing is a nickel microlattice. In fact, I'm going to hold it up here. This is sitting in my office. This right here is the very material that's sitting on top of this dandelion. And you can see it's hardly perturbing it at all. And this was a collaboration with HRL.
Excuse me?
Yes, hopefully. Okay. So it was the world's lightest material for about 3 weeks until the graphene aerogel guys blew us out of the water. This is to show you that it is possible to apply the concept of architecture to make very, very lightweight materials. And in fact, what I'm showing you now are some of the nano-architected materials that were made by students in my group. And you can see that one of the reasons for why they're black and white is because we've reduced their dimensionality by 3 orders of magnitude. So these are all nanometer scaled and low, maybe 1 to 10 microns length scale. So for the reason why we had to reduce this dimensionality is to get to the simultaneous attainment of the lightweight and the mechanical resilience. So at the micro scale, they're still not resilient. And I'm going to walk you through for why that is in a minute. What I wanted to show you here is that we're not limited to periodicity. And this is an important aspect of this nano-architected world. For example, in the southeast corner, you'll see the micro TARDIS. Those of us who are fans of Doctor Who, they're about 1/1000th of your hair diameter. You can see that we can make fractal or nanofractal types of architectures. You can see we can make woven architectures, and you can see that we can build in various density gradients within the same structure. Now, there's the obvious level of porosity here, and that is that these are all so-called porous or cellular solids, so you can see the empty space. The less obvious level of porosity is that if you take a look at the image to the left of the TARDIS, is that there's a beam that's hollow. And if you can see the scale bar, the thickness of that wall is about 10 nanometers. So these materials embody every length scale from some nanometers to some hundreds of nanometers to microns, and maybe eventually to the macro scale. And because of that coupling at the nanoscale between the mechanics and the material properties, we call these metamaterials because their properties can no longer be described fully by the mechanics perspective or the materials perspective. Now, hopefully I've convinced you at this point that they're very lightweight, but I have yet to show you why we might expect these materials to be stronger. What I'm showing you here is yet another log-log plot, and this plot represents the strength of many different common metals, so like gold, like silver and nickel, etc. What this plot shows us is that in their single crystalline form, all metals become stronger when you reduce their dimensions down to about 100 nanometers. So that tells us that gold or copper, something we know to be very malleable, becomes as strong as steel when you reduce their dimensions to the submicron level. Now, when I said in their single crystalline form, I don't mean that they don't contain any defects. I don't mean that they're pristine. What I mean by that is that they don't contain any grain boundaries. And now we have this power law scaling. Of course, this is a log-log plot, right? Now, the size effect is more nuanced than that. And that is if you look at the same metals like nickel, like platinum, etc., and now you deposit them using a different technique, for example, CVD or PVD or any kind of sputtering in its thin film form, for example, now they contain grain boundaries. And all of a sudden, this effect is reversed. And now what you can see is that smaller is weaker. It's a more modest size effect. It's not plotted on a log-log plot, but it's non-negligible. Now, the size effect is even more interesting than that. If you look at a brittle material like glass, for example, what I'm showing you here is a uniaxial tension experiment on a 75 nanometer wide glass rod. And you can see that it's first forming a neck prior to fracture, and it extends by about 100%. So at room temperature, we all know glasses are not supposed to do that. So yet another interesting effect that emerges at the nanoscale. And this is the last example. So when you look at a ceramic nanolattice, and this is a single unit cell, and what we're doing here is we're deforming a single unit cell, and we're observing that these very brittle ceramic beams are bending without fracturing. And if you were to calculate the stress, the tensile stress component within that beam, it's 1.7 gigapascals. So ceramics are not supposed to stay intact when they're being tensed with that much stress. So what this is teaching us is that sometimes materials can get stronger, some other times they can get weaker, some other times you can suppress brittle failure. But all of these phenomena occur only at the nanoscale. And so the big question in our group was, can we harness all of these beneficial properties and then proliferate them onto the larger materials with larger dimensions? And for that, we are utilizing this concept of architecture. And the way we would proliferate these size effects is by utilizing three-dimensional lithography. So this particular form of 3D printing or additive manufacturing is called two-photon lithography. And the idea is that in a single laser pulse, there are exactly 2 photons that are released, and then the constructive interference provides a sufficient amount of power to cross-link a photosensitive resin within a small volume, and we call that a voxel. Now, this voxel is rastered in 3-dimensional space without a mask or without any kind of light-based interference pattern, for example, so that we can write a nano version of each one of you without using any kind of alignment, without using any kind of mask. It's just effectively writing the pattern. And here I'm showing you a real-time video of one of the nanolattices that my student is writing. So you can see it's not a very slow process. It's certainly doable to make many samples per day, but it's not quite at the manufacturing speed. So for that, we developed a different technique, and this one is in fact based on interference lithography. So this is a collaboration with my colleague Andre Faraon, who works on metasurface masks. And the idea is that it creates a 3D interference pattern with light. And now these points of high intensity that you see here can be translated into a photosensitive resin and then cross-link the polymer in a similar fashion as the 2-photon lithography, but in a single laser exposure. And the advantage of that is that we can now make effectively sheets of paper. So what you're looking at here is effectively an inch by an inch sheet, which in our world is very big. And when you create a cross section of it, you can see it's fully nano-architected all throughout its thickness with a pitch of about 500 nanometers. So this technique allows for scalability and allows for fast production of nano-architected materials, but you can no longer write arbitrary shapes. And so you can already see this trade-off is that in the 2-photon lithography world, complexity comes for free, but it takes some time. And then this is just to show you the regular 3D printing type of an approach that we have. You can see we can write very poisonous gummy bears that look very similar to the real ones. And so this is just to show you how much control one can have in terms of this tunability of the resin and the laser light interference. Now, the way we conduct our experiments, of course, is requires having some kind of an electron microscope, because everything we work with is either at the nano or the micro scale. So this particular instrument, called Cementor, allows us to conduct in situ nanomechanical instruments while observing the deformation. So it's an instrument that's similar to a nano-indenter, except it allows for the compression and the tension experiments to be conducted. And just to show you the broad range of the length scales that we're able to probe. So this sample right here, for example, is 100 nanometers in diameter. And so we make our own grips that can pluck them while measuring the stress strain response. And then these are carbon nanotube forests that can span hundreds of microns. So there's quite a bit of range that we can access and probe. So let's get back to our hypothesis. And the hypothesis was, can we utilize the size effect and then proliferate it into materials with larger dimensions by utilizing this concept of architecture? So what I'm showing you here is an octet nanolattice that's made out entirely of alumina. So I imagine many of you are familiar with ALD, atomic layer deposition, right? And so when we talk to our friends who are the ALD experts, they said, oh yeah, we can deposit conformally anything you want as long as it's alumina. So here's the alumina nanolattice. Now the wall thickness here is 50 nanometers, and it's very brittle, right? Most of us know that alumina is a type of a ceramic, and it's very brittle. Now its relative density is something like 1%, maybe less than 1%. So it's mostly air. So think of your coffee mug with a severe case of osteoporosis. So we know that when we apply pressure to something that's very porous and very brittle, it's going to collapse and certainly not recover. We have a little nanosymmetry in our instrument, and that's exactly what we're observing. Now, so it crushes and dies. I mean, part of being at Caltech is that we don't really give up. So our student is pretty resilient as well. So this is the work of my former student, Lucas, who effectively repeated this experiment. But now the only difference is that the wall thickness is reduced by a factor of 5. So now these walls are not 50 nanometers thick, but they're 10 nanometers thick. So if you were to just project based on what we saw in the previous experiment, it should crush and die even more readily, because now the walls are even thinner, and it's even more probable that this very brittle nanolattice is going to fail. So let's see what happens. And what we're observing here is that this very brittle, very ceramic nanolattice is being compressed to almost 50% and then fully recovers. So if that doesn't convince you that there is in fact a size effect, there's no point in continuing with this seminar. So this was the introduction to basically bring all of you into our world where we're very interested in the nano-induced size effects in materials and how they can manifest themselves at the larger scales. So we've learned a lot since that point. And so one example here that I'm showing you here is that this recoverability of brittle nano-architected materials spans beyond the periodic architectures. And you can see that on the left-hand side, it's something that may look like trabecular bone to you or something like that. So this is not beam-based. This is entirely shell-based, and it's entirely curved surface-based material, and all made of alumina. And you can see that this recoverability prevails over many, many cycles without any visible damage to the structure. We also observed that when you introduce density gradients into your design, like for example is the case on the left here, you can see that the bottom portion, which is less dense and therefore more compliant, fully compresses and densifies before the top portion even realizes that it's being compressed. And you can see that being reflected in the stress strain data as well as in the deformation behavior. So you can see these plateaus. And that allows us to design materials where we can pre-build the trajectories of failure or the trajectories of deformation. Turns out that they're particularly, these gradient type nanolattices are particularly efficient in supercapacitors by how they create extra contact points if the breakdown voltage were to be attained. So there are many other side effects that seem to be useful. This is the deformation of a fractal nanolattice where each beam is now comprised of self-similar unit cells. And you can see that it's kinking in the lowest degree of hierarchy. And we're expecting this fracture to initiate in exactly that point where the stress concentration is so high. And very unexpectedly, this kind of structure also fully recovers. So what that tells us is that this recoverability can be attained under complex stress states and in very complex geometries. So that's what we learned about hollow materials. And this is very important. These are all made of hollow elements. Now, of course, trying to understand why this happened, one we call to mechanics, and one type of deformation that allows for this kind of recoverability is called shell buckling. So imagine your soda can effectively, right? So you basically create some wrinkles in the surface of the hollow cylinder, but then you have the ability to recover. And when you perform this calculation, it turns out that there's a critical T/A ratio. So the ratio of the wall thickness to the radius, which for this particular material, the ALD alumina, turns out to be something like 0.03. So the idea is that if you're below that ratio, your structure is able to recover based on this shell buckling criterion. And then above this kind of ratio, then your material will fail prior to the structural response. And so let's see what we're observing. So for the 10 nanometer wall thick materials, this ratio is 0.016, so it's below 0.03. And you can see that every kind of sample recovered, and these are different, the different colors represent different sizes of the unit cell. And as we increase the wall thickness and the first approach and then supersede the critical T/A ratio, you can see that the deformation becomes a lot more stochastic, a lot more catastrophic, and these nanolattices are no longer recovering at all. So it turns out that the answer lies in mechanics. Well, if that were true, that means that if we were to construct a building where each wall is now represented by maybe 10 centimeter thick tubes, and the radius is 3 meters thick, wide, and then the whole building maybe spanning multiple kilometers, we should observe the same response, right? It turns out that if it turns out that everything is about the T/A ratio, right? Well, hopefully you're all smiling because, of course, this would never happen, right? If some giant came and stepped on this building would never recover. So the idea here is that why does this happen at the nanoscale, but not at the macro scale? And of course, the answer lies in defects, right? So we all know brittle materials to fail at flaws, and the probability of finding a flaw, maybe thousands of flaws, hundreds of thousands of flaws in something that's this large is 100%, whereas in something that's only nanometer sized, first of all, the size of the largest flaw is only 10 nanometers or whatever that thickness is. And then just the probability of finding a flaw is much, much lower. So what this is teaching us is that if we were to fill up the same volume, like a room, for example, with a nano-architected material versus just a regular fully dense material, we're going to get a much better material properties in the nano-architected world. Okay, so then the next natural question that came up was, can we utilize this kind of an approach in creating non-hollow structures? Because as you might imagine, it's actually quite challenging to etch out the initial scaffold that was so painstakingly written. So we turned to carbon. Carbon is stiff, carbon is lightweight, carbon should be a perfect material to make monolithic based nanoarchitectures. So what I'm showing you here is a carbon micropillar, right? We all know, we write with graphite, right? We all know what happens when you push on the pencil too hard. And of course it would crumple, right? So here's our pencil lead effectively, and we're compressing it. And this is very interesting. We're already at the stress of 5 GPa. This is gigapascals, right? Like, so this is very, very high compressive stress. And what this guy is doing, it's bending, it's certainly not enjoying itself, but it is not fracturing. And this is very, very counterintuitive because we all know, of course, glassy carbon to be very brittle material. So this is encouraging, right? So we are learning that maybe the monolithic building blocks are still going to work. So when we perform the microstructural analysis in the TEM, what we're observing is that what gives rise to this recoverability is the presence of graphene-like curved fragments that are sp2 hybridized carbon, effectively, and the local transformations within these localized regions are able to accommodate the globally applied axial strain. And so we collaborated with a group at Tsinghua University that were able to model using MD simulations the same kind of microstructure. And sure enough, what they showed is that it's the coalescence of these so-called hotspots within the pillar structure that allows this these localized deformations to accommodate the global straining. And as my old advisor would say, don't believe anybody who tells you about ductility and compression. So what you see here are some tensile experiments that show that sure enough, even under tension, these carbon micropillars and nanopillars are extendable by at least 20%. All right, well, so here we are. We learned all about carbon that we needed to learn. And so at that time, we decided to architect with these carbon nanoscale building blocks, since we know now, so we discovered at that time that they were deformable. And what we learned is that that basically we're not going to get any recoverability in these kinds of nanolattices, no matter what we did. What we're comparing here is an isotruss lattice, which is supposed to be the stiffest and the strongest, to an compared to an octet lattice, which was very stiff, and every time at every relative density, every time they brittly failed. And the reason for that, of course, is again because we can't underestimate the role of defects. So here, what we're learning is that even when the individual nanoscale building blocks are deformable, you can't just simply go and start architected with them because you're going to have to worry about the structural defects. So defects are super important. Okay, so just taking a pause here just to show how far we were able to get. So this is the original white space that we wanted to explore originally. And all of these kind of elongated domains are some of our earlier work. So this is so a decade ago. But you can see right away that, for example, the hierarchical nanolattices were able to buy us 2 extra orders of magnitude reduction in relative density. So there's plenty of potential, and certainly we and maybe many other groups can get much farther into the white space now. We learned that in tension, the specific tensile strength of these alumina nanolattices is supersedes that of, say, balsa wood, which is a material you would use for kayaks or for any kind of lightweight sports equipment. So there's a lot of promise in that. We learned that carbon, the very brittle carbon that still didn't recover, turns out that it has additional benefits. For example, it's the only material that gets close to the theoretical limit at the higher density regime. And so this is a very interesting finding. And in fact, I want to spend a little bit of time validating carbon. So it turns out that we just weren't doing the right experiment. Like I said here, quasi-static deformation is not microarchitected carbon's forte. So what my former student Carlos did is he subjected these carbon nanolattices to impact. And so these would be high strain rate experiments that are called lipid. So this is laser, right here, laser impact projectile impact testing. And so you could see that, I don't know if you saw the video, I'm just going to play it one more time. Right here, you could see the impactor, which is a silica microsphere that's rebounding from one of those carbon nanolattices that Carlos made at that time. And the 3 types of response that we observed were elastic response, where the projectile fully rebound, projectile capture, where the projectile was embedded, and then projectile rebound. And that is where it left a crater, but it rebounded back. What we never observed was any kind of behavior where the projectile penetrated through to whatever this nano-architected layer was protecting. So this is a very promising impact mitigation strategy. And in fact, if we were to plot the specific inelastic energy as a function of impact velocity, you can see that we're comparable, that this nano-architected carbon performs similar to Kevlar, if not outperforming some of the traditionally used composites for energy absorption. And the plots on the left are showing this impact mitigation for the rebound energy versus impact energy. So you can see the plot on the top is 14% relative density, and you can see that it gets close to ideal impact mitigation versus 23% relative density. And that one, you can see how much the relative density of the nano-architected material really contributes to its impact mitigation. So we were pretty excited about this because it turns out nano-architected carbon absorbs quite a bit of energy. I wanted to spend just a few words on this energy absorption capabilities. So we collaborated with my colleagues group, Andrei Faraon here at Caltech, who created these metasurface masks for us. And then we built a laser interference setup where in a single exposure with a green laser, we're able to produce this entire nano-architected field, which you see here. You see this cross-section here. And after we produced these nano-architected sheets, my student Kevin put them into composites. And so you can see that layering these composites and interpenetrating these nano-architected layers allows us to further create a composite material, now utilizing these nano-architected layers as structural components. After that, Kevin subjected them to a few experiments in the Hopkinson's bar. So these are the special high-rate experiments. And what we're observing is that, for example, the layered composites, something that we would expect like a layered cake, quite literally, something that we would expect to collapse in a layer by layer fashion and therefore offer greater energy absorption, doesn't actually offer that. Instead, we're seeing much amplification in terms of energy absorption when the composite is interpenetrated. And that now makes sense because now we have this energy transfer mechanism and the load redistribution mechanism available to us when the nano-architected components are able to more efficiently redistribute the stress that they're experiencing. So this was a very good learning for us, and this was a very important learning for us because we're showing the way of how these nano-architected composites can be utilized in real personnel protection applications, for example. So this is something that we're quite excited about. Spending just a little bit of time on tensile behavior, showing that, for example, that the nodes in these nano-architected materials, one thing we really need to worry about is the nodes. Like we saw failure in the carbon materials, same thing is true for the tensile experiments. And so you can see that almost every time we performed a fracture experiment, it fails at these nodal planes, and that's where the damage is accumulating. This is true even in compression. And so what you see here are some of the damage that was built at the nodes in individual unit cells. And so my former student, Weedy, decided to completely do away with the nodes. And he came up with these interwoven and woven nanolattices, where now none of the individual strands are contacting one another. And you can see they're interwoven. And so the only, I guess, force that's holding them together is a force of friction. And so what we're showing you here is the side-by-side comparison of the tensile deformation of the woven nanolattice. So you can see that on the left, it's very, very extendable. Well, of course, the regular nanolattice on the right broke. And because the original one didn't break, we can do the compression experiment on exactly the same specimen, which is not true for the specimen on the right. And you can see it compressing, both of them compressing, and you can see how much more energy this material is able to absorb. So what we're learning is that the interwoven approach, where you do away with the nodes, which of course are the culprits for damage accumulation, you can get to much greater strains and make much more compliant materials. Now, this is just to show you some of the modeling that shows us that what's really important here is the combination of the R over L, which is the slenderness ratio of each individual strand that's effectively braided together, and the overall thickness of each interwoven beam. And so now we can really control it. We control the stiffness, the bending stiffness, and the axial stiffness. Now, Weedy took this one step further. He decided that instead of just focusing on the interwoven materials, he's also going to probe the knotted materials. And so this is my former student, Max, who loves rock climbing. And so you can see this is the standard figure 8 knot. So what Weedy did is he created a knotted architecture where a single strand subtends the entire unit cell and comes out on the other end. And then the woven architecture where you still have the exit and entrance points at the top and at the bottom, but now it doesn't span the entire unit cell. And so now watch what happens. So the knotted one is on the left, the interwoven one is on the right, and you can very clearly see that they first start deforming in exactly the same way. And after that, the regular one just becomes very stiff because we're starting to strain it, whereas the nano-knotted one shifts into the friction-dominated regime where we're effectively working against the friction force and tying the knot. So this taught us that at the nanoscale, we actually have a novel energy absorption mechanism available to us, specifically tying the nanoknots. And so this was, you can see as the area under the curve, of course, how much more energy we're able to absorb here. So this is also another way that offers us, for example, the possibility to study friction at the nanoscale. So the mu here, the mu component here is the coefficient of friction. And I will challenge anyone who will tell me that the coefficient of friction or the friction behavior at the nanoscale is exactly the same as that at the macro scale. So it's definitely something that needs to be taken into account once we start dealing with the surface forces and with the surface chemistry. And so this is already some glimpse into that behavior. So it turns out that the product of the coefficient of friction and the Young's modulus is actually what's important. And so what we did is we treated the surfaces using different ways. So for example, as fabricated versus UV treated, and you can see that that iso line is actually shifting towards a higher mu over E. So this is a great opportunity to study friction at the nanoscale. All right, and I have about 10 minutes left. So I'd like to shift a little bit more into the additive manufacturing world and to show you what this enables us, like what all of these seemingly mechanical pursuits have enabled us to accomplish in terms of additive manufacturing. So one first thing I would like to share with you is a biomedical application where, for example, now that we know that these interwoven materials can be tunable in terms of the stiffness, we would like to start making microneedles that can release different types of drugs out of them, because now we can fully maximize, maybe triple the surface area while fully tuning the stiffness. So what you can see here is an array of microneedles that we're hoping will be able to deliver either a GLP-1 type of a drug or insulin or something like that, so that we can maybe contribute to controlling people with obesity or people with diabetes. So this is controlling the management of those, both of these conditions. I wanted to also show you the application in energy storage. So here's our work that shows us how we would make batteries using this approach. So this is the work of my, again, former student, Yutrin Sun, who is showing that we can create cathode materials and anode materials. And so this project specifically is micro-architected oxide. So this is lithium cobalt oxide, which is a cathode material. And what Yutrin did is she wrote this blank hydrogel, and then she infused it with metal salt solutions, for example, in lithium nitrate and cobalt nitrate. And you can see that after a certain thermal treatment and calcination, she was able to produce the lithium cobalt oxide microlattice, which bears uncanny resemblance to the CAD design one. So you can see the SEM, the optical image and the CAD produced image overlaid on top of one another. So Yutrin was able to characterize this as a battery performance, and sure enough, this paves the way for maybe more efficient solid state batteries sometime, and they're quite robust. What Yutrin was able to also demonstrate is that she can get to the dimensions that are much smaller than the ones that have been reported before. She can push them down to about 40 microns and even below, whereas all previous reports show hundreds of microns thicknesses. So this is making it possible for us to make much smaller battery electrodes. What Yutrin also demonstrated is that their mechanical properties very much depend on how they were produced. So this particular mechanical experiment shows us the engineering stress that's very low, right? So it's about 50 kilopascals. And in contrast to the same electrode that was treated at a different temperature and has and different pressure, that shows an order of more than an order of magnitude enhancement in the mechanical resilience. So you can see that this post-writing thermal treatment is also very, very important. We've been really interested in using machine learning in designing these architectures. Sometimes I very often get a question, well, how do you choose your architecture? So here's one way of how we can choose it. It depends on what parameter you're trying to optimize for. And one of these parameters can be stiffness. And so what we're showing here is a model that provides so it's a forward model and an inverse model that predicts the architecture to meet a particular stiffness goal. So this is our collaboration with Professor Dennis Koopman, who basically developed the model. And then what my student did is she reconstructed trabecular bone. What you see here on the left is an actual tomography of trabecular bone. And then she was able to print both the reconstructed bone and the AI-generated sample. And then she was able to measure their stiffnesses. And so what you're seeing here is the real data that shows that they are, in fact, anisotropic. And that's not something that you could have easily predicted by simply looking at this structure. In fact, most people who would look at this structure would think that it were isotropic. And so this was something that was a really neat application of machine learning. I would now like to move on to introduce a particular additive manufacturing strategy that we coined hydrogel infusion additive manufacturing. And I already gave a little bit of a hint to it when I showed you how we made the oxides. And so the idea here is that if you have the right cocktail of photosensitive, photoactive molecules, and then you infuse the metal salts into it, you can get this hydrogel that's swollen with the metal ions and then subjected to thermal treatment, which will ultimately give you the metal oxide and eventually the parent metal. So what we're showing you here is the work done by my former student, Max Saccone. And these are not computer-generated images. These are actual real images of samples that he created. You can see it's a very pretty project. He was able to make a single component metals like silver and nickel. He was able to make alloys like copper nickel. He was able to make high entropy alloys like this multi-component alloy, as well as materials and metals that are very hard to form, like tungsten, for example. And so what we learned from that work was that one-pot vat polymerization offers a lucrative and very efficient way to create nano and micro-architected materials made of metals and metal oxides. There was an added bonus that we didn't plan for, but it and actually this work is just got accepted, that shows that the interesting kinetically driven microstructures that are formed in this process give rise to much greater strength. So what we're showing you here, I know it's a busy plot, but the message to take away here is that these additively manufactured metals turn out to be a lot stronger than the same metals produced in a conventional classical way. So it's basically we're bringing metallurgy to 21st century here by enabling this new approach to metal fabrication. Okay, this is just to show you that we can push this high-end approach into the nanoscale. And so not just the microscale, but the nanoscale. And this is where, of course, we're using 2-photon lithography. It's a slightly different cocktail. And my former student Wengshin was able to still infuse it with metal-containing salts. And we were able to get these tiny, 200 nanometer nickel, for example, nanopillars. You can see that they have every kind of microstructural feature in them. These are TEM images that show the cross sections. And so you can see they're nanocrystalline, they're nanoporous, they're very interesting. And then also, in addition to being interesting, we conducted these uniaxial compression experiments on them. And what we learned, I'm going to skip through all this. What we learned is that these red points are what we measured. And so what we learned compared to all the other nano-sized nickel is that these nano pillars were stronger and less susceptible to the size effect compared to all of their counterparts. And I'd like to take a little bit of a pause here because there have been people working for 2 decades now, actually, since 2005 or so, in this field. And this was kind of everybody's understanding is that nano-sized metals always exhibit the smaller, stronger size effect if they're single crystals, or smaller, weaker size effect if they're nanocrystalline. So what we're learning here is that you can actually fully suppress the size effect by the right composition of nanocrystallinity and pore distribution. So the size effect is something that not only can be tuned, but can also be suppressed. So this was an interesting observation for us. Okay, and then the last few minutes, I just wanted to share some of the non-metal work with you. So we've been very interested in the soft materials as well. And so this is the project conducted by, again, you can tell a lot of my students just graduated. My former student, Sola, who effectively used these so-called metal polyelectrolyte complexes to 3D print hydrogels with different metal ions infused into them. She didn't thermally treat them after to convert them into anything. Instead, she utilized this concept of dynamic cross-linking, where the bonds that are formed between the metal ion and the polymer backbone are non-covalent. And so the formation and the dissociation of these bonds, as well as the local pH environment, gives this very intimate coupling between chemistry and the mechanics of these materials. And I'm going to show you these two videos. So the one on top is infused with calcium, which is a divalent metal, of course, and the one on the bottom is infused with aluminum, which is a trivalent metal. And you can see from this highly technical experiment that the aluminum one is very stiff and not very stretchy. And the calcium one, again, it's the same resin, the same polymer resin, but infused with a different metal ion, is very stretchy. Now, in more technical terms, we now compared the divalent to the trivalent to the monovalent response. And you can very clearly see that that's a key parameter that makes a huge difference in the mechanical response. Now, the bottom, the x-axis label is not a mistake. It is, in fact, 1000% strain. So you can see that these materials are extremely stretchy and can be made extremely stiff, like is the case in the aluminum. We collaborated with another group at Caltech. This is a theory group in chemistry, and they are able to explain this kind of behavior. So the trivalent metals tend to coordinate in these clusters, and that makes them more stiff, and that makes them be more susceptible to fracture, but at a much higher stresses. Whereas the divalent metals are, they only coordinate in two different places, so that enables them to sort of slide past one another, and that gives rise to the stretchability and tremendous extensibility. So this is just to show you that depending on the pH, we can see space separation versus homogeneous space formation. So it's a true representation of chemomechanics. You can see the profile of the two different phases, the polymer phase and the water phase. So these are hydrated gels, of course. So this is something that can be used for biomedical applications. And then the last thing I'd like to share with you is that, so with some mechanical modeling and recognizing that these hydrogels infused with different metal ions have different time constants, allows us to really control their reconfigurability. So what I'm going to show you here is the deformation of a bilayer strip. So the aluminum is on the left and the nickel is on the right. So again, it's the same polyacrylic acid based resin. And now it's infused with aluminum on the left and nickel on the right. And what I'm showing you on the right is like, on the top is the compression experiment, where you can see this bilayer strip buckles, as we would expect, to the left. Now the deformation rate here is 0.02 per second. Now, if you conduct exactly the same experiment and exactly the same strip, but you really slow down your deformation, you can see still very much that it's buckling, but now it's buckling fully to the right. And the only difference between these two is the strain rate, which means how fast are we deforming them. In the next experiment, this is the so-called stress relaxation experiment, we effectively subjected this bilayer strip to a hold. We attached a load to it, and then we held it for 10 seconds. And then when we release the load, you can see that it's curling up. And then if we were to hold the same strip for an hour, you can see that it's curling up to a much greater degree of curvature, a much tighter radius of curvature. And so that gives us a degree of tunability and degree of responsiveness in these kinds of impact materials, which already represent a pretty unique set of materials. And this is just to show you that if we program the shape, for example, a blooming flower, and you can so here's the calcium versus aluminum comparison. So we're going to place them down into the pre-programmed shape, and you can see that they're both blooming back to the initial shape, but you can see the rate at which they're blooming is very different between the two. So you can start thinking about how you can make actuators and active materials using this approach. Okay, I think it's 12:47, so I think it's a good time for us to stop. So I think I'm just going to skip through the end here, and I'm going to reshare my screen. Hopefully everybody can see my screen now. All right, so now we're getting to the end of this presentation, and this is a very relevant video, near and dear to my heart here. And I think basically the question is, well, so what, right? You showed us all these interesting, hopefully you found them interesting, phenomena, all these maybe fun videos and phenomena. So what? What's the big deal? And I guess the message I'd like to leave you with is that if you're careful with tuning 3 very critical parameters, one of them, of course, is material architecture. Are you building something that's a closed cell, open cell type of a architecture? Are you interested in energy absorption? Are you interested in catalysis? Are you interested in electrochemical response, maybe microelectronics response? All of that is really intimately governed by the architecture of what you're making. The second one, of course, is the nano size effect. Every class of materials exhibits a size effect, but that transition length scale is not the same for every class of materials. And then the third one is the atomic level microstructure. Is your material amorphous? Is your material crystalline? Is it nanocrystalline, etc.? So understanding the combination of these 3 for each material class will enable us to create entirely new classes of materials. For example, we can live in the world where there will be no hearing aids because we'll be able to just write the cochlea bone directly and then populate the cells onto it and simply insert it in the ear. Your iPhone 83 is not going to need to be recharged for about a year and stay in a single charge. Our balloons will not need to be filled with helium because these are very lightweight, very stiff materials, so we can just evacuate them. Vacuum is lighter than air. Not very relevant for the season, but here are some Christmas ornaments, and of course we can suppress the shattering of these. And then this is my favorite example here. And we all love chocolate. So our latest, greatest pursuit is making chocolate nanolattices that are 100% taste, 99.9% air, and 0.01% calories. And so with that, a big thank you to you, a big thank you to my group and all the funding sources. And I think you just kicked me out.
I'm sorry, Julia, I didn't mean to kick you out. What I meant to do was control the screen sharing so that only the host and co-host could share so that we could prevent any more incidents. And I thought you were a co-host, so I thought you were going to stay up here.
Do you want me to? I mean, I'm not really sharing anything other than my lovely group. Sharing is not turned on.
Let me see if I can fix that. Sorry about that.
No worries, no worries. Please
Let me go ahead and say thank you, Julie. That was fascinating talk. I really learned a lot. A lot of questions come to my mind, we're going to try to take questions as well. We'll take audio questions only. But let me start. I was intrigued by a lot of it, but the knot tying aspect I found fascinating. Have mathematical topological theory been applied yet to that? Because there might be some opportunity there for new structures based on topology.
You mean the topological insulator, those kinds of effects?
Yes.
Yeah, we'd love to do that. I think they're still a little bit big. I think for us to see these kinds of effects, we're going to have to get down to maybe 10 nanometers and below. So we would very much welcome that kind of research, and we've tried. We've actually had some discussions with the folks in physics here who work in topological insulators. And I think once we're able to make these architectures at the 10 nanometer level out of the semiconductor materials, I think there's a very clear pathway for how we can study them. So that's definitely something very interesting and very worthwhile.
Very good. I think we'll proceed with some Q&A. Steve, are you in control? Can you unmute questioners? Is that how we're going to do this?
I think everybody's unmuted now. I'm going to let Priya ask a question because her hand is up, and then I'm going to mute all.
There we go.
Yeah, now you're back. After Priya's question and Julia answers it, I'm going to mute all, and I'm going to unmute Julia and then look for hands to go up, and I will unmute any other questioners.
Thank you.
Okay, Julia, fascinating talk.
Thank you.
I was really hooked from beginning to end. The question that I had is like for the initial measurements with the carbon nano lattice, I was wondering how you make the measurements in the SEM, because it looks like there's some kind of apparatus that allows you to push down the lattice and pull up the lattice, and I've not seen anything like that. So would you be able to share how that's done?
Yeah, absolutely. That's we have an in situ nano-mechanical instrument that we built that allows us specifically for that purpose. We actually have 2. So one of them is a nano indenter-like attachment inside of an SEM, And the other one is a modular one that you can put in any kind of we have it in the focused ion beam in the fib in our instrument, but you can put it in any SEM. So there's a company called Femto Tools that we really like. There's a company that's called Nano-Mechanics Inc. or something like that. There's also Alumnus. So there are a few companies, maybe 3 or 4, not a lot, but some specialized companies that make these in situ probes that you can put into the electron microscopes that will allow you to conduct these kinds of characterization. We built our own.
Thank you.
Thank you.
But I can say that at least we now know why you titled it Intelligentsia, because it's a
well, it's just, yeah, thank you for recognizing. I really appreciate that. It really paves the way for how materials can behave. I mean, we're not at a point yet where they can be autonomous in the sense of making their own decisions, the materials that is, but we are at a point where you can think of like computers, for example, right? Or 3D logic circuits, or for example, we just had a collaborative paper with Wei Gao's group here at Caltech, which showed these nano robots that can travel to a particular tumor and then release the drug in the specific site and then be bioresorbed. It really opens up our whole world in a way that I think hasn't been possible before. So we're very much enjoying doing this kind of research. So thank you for acknowledging that.
Well, I just my sense, just hearing everything you said, that it's just the beginning.
Exactly.
And I'm really excited to see where it goes from here.
Thank you.
Any other hands?
I need some funding.
Yeah, of course. Yeah, need to start that flow of funding again.
Oh man, we really do.
Any other questions? Then maybe
there is one in the chat window from Jamie Bravo from the Moses 2.0 team. I'll summarize it. Nanostructured metals have significantly better electrical conductivity than bulk metals for RFIC applications. Have you looked at testing the electrical properties? And a comment, the structure material reminds me of the clamshell's superior strength.
Yeah, this electrical conductivity question comes up from time to time. I think that that's more of a surface and the microstructure effect. So you can imagine the hypothesis being is that there's either more scattering or less scattering, right? So the electrical conductivity would be effectively still dominated by having grain boundaries in a material, in a metal specifically, right? So if you have a lot of grain boundaries, you're going to have many individual sites for scattering, and so your resistivity is going to go up. If you can control the grain boundaries, you can definitely control for that. I don't think that in any of our experiments that we've conducted so far, we've observed any kind of an electrical response, something that's unintuitive to us. So again, I think that we would have to set up a properly designed experiment, but knowing what to test. So my question to anybody who's interested in the electrical signature would be, what is your hypothesis for what you think is going to happen? Because in all the mechanical studies, it's very clearly the length scale of the interaction of a particular type of defects with the characteristic material length scale. So in bulk materials, you would obscure all the effects of small defects like dislocations or pores because there are just so many of them. So it's a collective, so we're observing collective behavior. And so it's not, we would obscure any interesting response there. Whereas once you get to these nanometer length scales, the effect of each individual defect is much more measurable. And so that's where all the interest, in my opinion, that's where all the interesting phenomena emerge. And so if we were to measure the electrical response, we would have to first identify what that length scale is, where we would study that phenomenon, and then we might uncover something for sure.
Very good.
Yeah, Julia, this is Ajay, and thank you so much for the presentation. I only heard half of it, but I had another meeting.
No worries.
I was also going to ask the same question about the metallic ions that you have in your polymer. To me, it resembles more like the conductive adhesives that people use for packaging, to replace the solder bonds. So the conductive adhesives are nothing but metal-filled polymers. And in your case, I felt that this is more of a structured oriented metal ions that are used. So I'm not sure how the conductivity of the metal ions are, But that would be an interesting area to study because they are much more structured. I mean, it also depends on the percolation theory as to number of ions that you're adding into the polymer. Maybe you're not having much polymers for them to have enough conduction.
Yes, absolutely. It's something that we can control. So the nice thing about all of these processes is that every aspect of it is something where you can really zoom in and target. Like, for example, incomplete pyrolysis, so that would be the thermal step, gives rise to the formation of a variety of different intermetallics, for example, different microstructures, different sintering behavior, different porosity, and all of these provide some measure of conductivity. And so you can start establishing, first of all, of course, it's correlation, right? But eventually, once you've correlated enough of them, you can build a kinetics model that can capture. It's a complex process because you have competing effects of reduction, for example, right? So you have the oxygen diffusion, sintering, where you have atomic solid state diffusion, where the grains may not be growing yet, but they're sintering, right? And so then you have a look at porosity. So this new paper that's about to come out showed that even under the thermodynamically driven force to fill in the pores, they still don't in alloys. So for the copper, there's certain copper and nickel compositions where the porous structure is more favorable because it's kinetically overdriven. So there's a lot to learn. I would say this. I would love to work with somebody who really knows how to do kinetics modeling, because I think we're going to start understanding many of these processes at the relevant length scales. So right now we've gotten to the atomic level length scale, collaborating with all the molecular dynamics people, for example. And of course, we are breaking down every continuum theory, but we are trying to uncover where that transition occurs. But that mesoscale is still very elusive. So if anybody would like to join forces, I would very much welcome that. I'm very easy to find. I think I'm the first one on Google if you look up Julia Greer.
Okay, very good. Well, thanks again for a fascinating talk. And I would like, is there another?
I'm sorry to interrupt. There is one more in the chat if you're willing to take one more. We are at the top of the hour.
Absolutely.
Okay, thanks.
Good.
How can the integration of hydrogen as an additive in 3D printing processes improve material properties and sustainability? And what challenges might arise in optimizing this technology for widespread industrial applications in regards to the HIAM?
So HIAM. Yeah, the scale, if I understand the question correctly, it's always the scalability, right? How do you scale these materials up? How can you use HIAM at the industrial length scale? My vision for this is that you really are going to have to build these additive manufacturing facilities that are the size of a football field, because otherwise the economy of scale is just not going to be there, right? So you're either, like I showed in the very beginning, in the interference lithography approach, you can get the speed, but then you're limited to a certain number of geometries that are all mask driven, right? In the 2-photon lithography approach, you can maybe design a very complicated part, but it'll be very expensive because you're making maybe like 5 of them, right? So I think that with the HIAM approach, that's actually the one that's most amenable to scalability, because you just need a very large 3D printer. You infuse it with metal, and it's a massively parallel approach. So you can infuse some, say you make 1 million samples in a single write, right? That's not so much time per sample. And then you can infuse some fraction of them with one metal, with another metal, convert some of them to lithium cobalt oxide, convert some of them to a metal, etc. So I think that HIAM, of all the things that I showed, is the most amenable to this, we call it massively parallel experiments, to kind of poke fun at our computational colleagues who say massively parallel computations. But I think that's where it would come from, that you can create many, a very large number of hydrogel blanks, and then kind of distribute them to the different functionalities, and kind of go from there. Because it's not the thermal treatment step, and it's not any step other than the writing one. So it's really how fast you can write the shape that you need.
Very good. Thanks for the very interesting question. All the questions very interesting, and I sense that we could stay here all night talking about more interesting questions. But let's all give a virtual applause to our speaker. And Amy has put up the schedule. There's no speaker next week. It's a holiday, but there's some great speakers in line. And I think she's going to put up a QR code. You can, if you want to be on the contact list for future speakers, please scan that code. And with that, I will say goodbye and thanks again to Julia and to everyone for their attention.
And thank you for inviting me.
You're very welcome.
Thank you, Julie.
Take care.
Bye.